Okay, so we're gonna start with a warm-up problem. The problem is whether the following three matrices are orthogonal matrices. The first one, U is 1, 0, 0, minus 1. %60%. Okay, the first one, most of you think this is true. That's yes. Because remember, if you want to check whether it is orthogonal matrix, all you need to do is to compute whether this is identity, in this case I2. The second one, if you're not sure, just to compute this 2 by 2 matrix. $10. Okay, so most of you think this is false, but some of you are not so sure. So the answer is this is false. The reason is, again, you compute U transpose U. In particular, the first column of U and the second column of U, they should be orthogonal. So let's just compute. U1 dot U2, this is cosine theta, sine theta, sine theta, cosine theta. So this is actually 2, this is 2 sine theta, cosine theta, or sine 2 theta. This is not necessarily 0. So may not be equal to 0. So this is not necessarily an orthogonal matrix unless this theta is 0, for example, or pi over 2. So it may not be 0. Third one, 0, 1, 1, 0. $10. Okay, this one seems to be simpler. Again, you just compute it and you'll find that this is indeed identity. Any question? So last time,
Um,
yeah.
sorry, the definition of orthogonal matrix is only like the columns are orthogonal, or both columns and rows have to be orthogonal?
Good question. So we proved before that if the columns are orthogonal, then the rows must be orthogonal as well. This is because, that's a good question. So this is because this means U inverse is U transpose, and therefore this is equivalent to U transpose is identity, which means the rows are orthogonal.
Okay, but only applies for squared matrices,
Oh yeah,
like
yeah,
n by n.
yeah. That's right.
Okay.
It's very
Okay, perfect.
important that U
Mhm.
is n by n matrix.
Thank you.
Okay, you're welcome. Okay, so last time we talked about the more general definition of the inner product. So let's say that if I have two vectors, UV, now they're not real vectors, but they're complex vectors. How do I define the inner product? So for the real one, it's UV equal to summation I from 1 to n. This is UI VI, right? When they're complex, I actually need to add a bar. So this is the proper definition of the inner product. You should check the properties 1 to 3, which is UV equals to VU bar. Indeed, you see that. If I exchange V and U, I need a bar to make them the same. And the U plus VW equals to UV plus UW, and so on and so forth. There's the fourth one. Yeah.
Sorry, could you just quickly go over what the bar means?
A bar, yeah. So bar means if I have a number z equal to a plus ib, where a, b are real numbers, then z bar is a minus ib, called the complex conjugate. Okay. So full is UU. This one should be non-negative. Why? So this one is UI bar UI, but this is just the norm, the magnitude of this, which is UI, treated as a complex number square. So Z square is defined to be a square plus b square, a complex number, and therefore this is indeed non-negative. If UU equal to 0, we have all the components are 0, and therefore U is the 0 vector. So indeed, this defines an inner product. Any question? Let me introduce some notation. If I have U to be U1, UN, that is in Cn, then when I write U bar, this means still a column vector. And this is UN bar. This is element-wise complex conjugation. When I write U transpose, this is UN, U1, UN, but viewed as a 1 by n row vector. If I write U star, this is the same thing as you first take a bar and then take a transpose, or the other way, the commute. This is U1 bar, UN bar. Just notation. Any question? using this notation, just like in the real case, now UV, I can write it to be U star V. Recall when UV are real vectors, I can write UV, which is the same thing as U dot V, which is the same thing as U transpose V. Now, in the complex case, I need to replace the transpose by the star because this is how the inner product is defined. Any question? So what's an orthogonal matrix really? So an orthogonal matrix and we say U transpose U equal to identity, right? So I have U, this n by n, this is equal to in. This is the same thing as saying if U consists of all the column vectors for the small u, and then ui dot uj, I consider as inner product. This one is 0 if I is not equal to j, and 1 if I is equal to j. This is literally meaning the same thing as on the left-hand side. So you can see this one really, so this is, defined in terms of the matrix operation, this transpose. But this one is fully generalizable. And I can talk about any inner product space. In particular, now if I consider U that is a complex, n by n, I can still adopt exactly the same criteria. But the definition of this inner product is now replaced by ui star uj. And therefore, this one becomes u star u equal to identity in the complex case, and this is called a unitary matrix. So unitary matrix is really the generalization of the orthogonal matrix, or most accurately, the real orthogonal matrix to the complex case. More specifically, since we have, let me just say, if U is U1, UN, then what is U star? I take, so this is U1 star, UN star, right? And so you can see that if U is a real matrix, this is nothing but the U transpose. Therefore, any orthogonal matrix the set of orthogonal matrices. So this is in the set of unitary matrices. An orthogonal matrix must be a unitary matrix. Any question? So we're going to use some of these things in today's lecture. So today's lecture, we really want to focus on the diagonalizability, go back to chapter 5 and talk about the diagonalizability of certain matrices. Because we know that certain matrices are not diagonal, like A to be 0, let's say 1, 0, 1, 1, and this is not diagonalizable. There are some other cases where if I have A to be 0, 1, minus 1, 0, right? This is everything seems to be perfectly real. And but the eigenvalues are lambda squared equal to -1 or lambda to plus minus I. So this is a real matrix, but the eigenvalues and eigenvectors are complex. So what we want to know is, I mean, how can we be sure that certain matrices are indeed diagonalizable, just structurally, and if better, the eigenvalues and eigenvectors are guaranteed to be real? And it turns out that there is a very positive answer to this question. That is what we're going to focus on, called the real symmetric matrix. A matrix A now belongs to n by n. It is called a real symmetric if A is equal to a transpose. Very simple. For example, so let's say A is 0, 1, 1, 0. Oops, only a tiny difference between these two. Okay, so this one, the eigenvalues are plus minus I. This one instead, so the eigenvalues are lambda squared equal to 1, means lambda equals to plus minus 1. And you can solve the eigenvectors correspondingly, they are real as well. So furthermore, they're not only real, if you just diagonalize this, the first eigenvector, so what's that? So that this one is, so this is 1, 1, or minus 1, 1, and therefore this one is, let me deliberately put a 1 over square root of 2 here, so that this is normalized. And lambda minus 1, again, let me deliberately put this thing here, it is 1 minus 1. So using this example, what we see, we have a few observations. One is the eigenvalues are real. Two is that these two eigenvectors, they are actually orthogonal to each other. So v1 dot v2 equal to 0. So before, remember, we only proved that if v1 and v2 correspond to eigenvalues, correspond to distinct eigenvalues, they actually are linearly independent. But now this is even stronger than independence. They're not only independent, but actually they are orthogonal to each other. Because I've normalized these two vectors, I can enhance this to be v transpose v equal to I2, where v is v1, v2. Because this is orthogonal matrix, it means that the inverse is just v transpose. Therefore, the diagonalization becomes A equal to v d v transpose, where D is a diagonal matrix lambda 1, lambda 2. Just a few observations. Any question?
Professor, what do you mean by stronger than independence?
Stronger means that if the two vectors, they are orthogonal to each other, then they must be linearly independent. but not necessarily the other way. Two vectors are linearly independent, not necessarily they're orthogonal to each other.
Okay, thank you.
Okay, so a big part of the rest of the class is to show that this observation, although made for this very simple 2x2 matrix, but actually they're true for general real symmetric matrix. And this is called the spectral decomposition theorem, or the so-called spectral decomp that you have seen before in Tony Stark. So how do we show this? One is, want to show so 1 to 3, they are generalizable to real symmetric matrix. First one, eigenvalues must be real. So let's see, I take an arbitrary eigenpair, AV equals to lambda V. Notice that at this point, I do not know whether lambda or V is real. But I do know that they exist, so I assume without loss of generality, lambda is a complex number and V is a complex vector. Okay, so this is the most general thing for, I mean, even though A is real symmetric, I need to assume that lambda and V can be complex vectors, just like the case you have seen here. It's real, it was not symmetric, but the eigenvalues are complex and the eigenvectors are complex. Any question? Now I want to show lambda must be a real number. If I can show lambda is real, I move to the left-hand side, then V corresponds to the null space of A minus lambda I, which is a real matrix, then V must be real by the Gauss elimination procedure. So if we can show lambda is real, then A minus lambda I V equals to 0, and this is real, then this gives V is in Rn by elimination. Any question? So this is the key. How do we show this? So, okay, so it's actually a little bit tricky. Let me start from AV equals to lambda V. Now I consider inner product. I consider inner product of this thing with V in the complex sense. Okay, consider this is the complex inner product. As we discussed the last time, once you have defined an inner product, right, you got this equipment, and then all the other things will just apply, like lengths, angles, projections, so on and so forth. And furthermore, I have, so I know that this is inner product, so this is lambda times V. So Now, the left-hand side, so this is equal to lambda v star v. On the left-hand side, this is v star a v, right? Okay, so now I got this equation, which is v star a v equals to lambda v star v. Any question? Now let me take a mysterious step, maybe, which is I put a star on both sides. Now I say, wait a minute, isn't this just a number, right? So this is a 1 by n by n by n by n by 1, and this is a 1 by 1, which is a number. So therefore, this star means just a complex conjugation. If you really view that as a number. On the other hand, star is not really just a complex conjugation, but it is both you do the complex conjugation and do the transpose. So remember that AB transpose equals to B transpose A transpose. Similarly, we have AB star is equal to B star A star. This is because you just do the transpose, I put a conjugation, conjugation applies to every element, and therefore I have this. Question? Good. So now I apply this rule to this. So I need to revert the order. So I start from this one. I have V star come here. Okay. So this V star is not this one, but come here. Then I have an A star. And then I have a V equal to lambda star is lambda bar because it's a number. And then I have, again, I have V star V. Question? We're almost there. So A is real symmetric. So this is A transpose. This is using the fact that it is real. Equals to A, using it is a symmetric. And therefore, A star is A. So this one is V star AV. This sounds familiar, right? Because V star AV equal to lambda V star V. So combined together, I have lambda bar, the conjugation, V, this is equal to 0. But this is a length. So this is the length of V squared. It cannot be 0. So we have lambda equal to lambda bar. What does lambda equal to lambda bar mean? If lambda is the real part is A, the imaginary part is B, then lambda equals to lambda bar just means that B is 0. So the imaginary part is 0, which means that lambda is real. So it's I would say this argument is a little bit more abstract and now seems quite technical. I acknowledge that. But the idea is very simple, that you want to show something is real. What you want to do is to show that one way to show that is this number lambda is equal to its conjugate. And using the fact that A is real symmetric allows you to make this part unchanged when you take the conjugation. And then you show that lambda is real. So this guarantees that for any real symmetric matrix A, the eigenvalues will always be real. Any other question? Any question?
Could you explain again how you went from V star, A star, V, and then to the lambda bar minus lambda,
So
like
you see,
that step?
yeah, so you see this part, V star AV is exactly this, right? But what's V star AV is lambda V star V. So
Okay.
lambda V star V is equal to lambda bar V star V, and therefore you end up with this equation. It's the product of the two numbers, so at least one of them needs to be 0. This cannot be 0, so this is 0.
Okay, thank you.
Any other question? Yeah, as I said, it's a bit technical, so I'm trying to go slowly with this. Okay, so the second part. The second part is that if I have two eigenvectors corresponding to two distinct eigenvalues, now due to 1, I know that lambda 1 and the lambda 2, they are real. Correspondingly, V1 and V2, they are real. And I assume lambda 1 is not equal to lambda 2. Then the claim is that V1 dot V2, because now they're real, I can write them V1 transpose V2 must be real. They must be orthogonal to each other. Okay, so let me say again that in chapter 5, we proved that eigenvectors corresponding to distinct eigenvalues must be linearly independent. Now we want to show something that is stronger. They're not only linearly independent, but they're actually orthogonal to each other. How do we show this? The idea is very similar to what we had before. We start from AV1 equals lambda V1 transpose, lambda V1. I apply V2 transpose to both sides of the equation. V1 transpose AV1 equal to V2 transpose AV2, lambda 1 V1, okay? And because this is just a number, I put it here. Now I apply transpose on both sides. Apply transpose. Then I have V2 transpose AV1 transpose equals to lambda 1. A number transpose is itself transpose. Now I use the fact that A is equal to A transpose. This is equal to V1 transpose AV2. And this is lambda 2 V1 transpose V2. Okay, so I got this equation. That's called equation 1. Now I look at this. This is AV2. This is V2. Oh, sorry. This is lambda 1. That's too fast. So AV2, as I said, equal to lambda 2 V2. So this is V1 transpose lambda 2 V2. So if we compare this part with this part, what do we get? We get lambda 1 minus lambda 2 V1 transpose V2 equal to 0. But I said lambda 1 is not equal to lambda 2 according to our assumption. we have V1 transpose V2 equal to 0. So they are orthogonal. And any non-zero vector, I can always normalize it, so I can even make them orthonormal. Any question? Again, these two proofs are not long, but if this is the first time you see it, they are quite technical. So after the class, I would like you to review this again and to really see how the transposes are used. So from the discussions above, we have essentially proved the following theorem, which is A is an n by n matrix. It's already real, so I only say it's a symmetric. So if assume A has n distinct eigenvalues, I said if, I'll discuss why I said this later. So let's call them lambda 1 to lambda n. We have proved that they are in R. Then the eigenvectors called V1 to Vn form an orthogonal matrix. And orthogonal matrix V, which is given by the columns of that. Remember, orthogonal matrix means this. Now let me further form a diagonal matrix, lambda 1 to lambda n. Then I have A equal to BD, V transpose. So now you can see that this is indeed a real symmetric matrix, because VD, V transpose. Transpose is the transpose of that is V. The transpose of a diagonal is diagonal, and so indeed A equals A indeed A transpose equal to A. Any question? So this is really just a summary of what I said above. The interesting part is that I made this additional assumption saying A is diagonalizable. I assumed A is diagonalizable. I even assumed that A has n distinct eigenvalues. This is a pretty strong assumption. But not necessary. To relax this assumption, this really goes beyond the Math 54. We're close to the end of the linear algebra part of this, this course. If you want to learn how exactly this problem is solved, in the general form, you should take Math 110. So let me just state the stronger spectral theorem. Without proving it. So if you are interested, you need Math 110. So if A is theorem, if A is real and symmetric, then 1, A is always diagonalizable. Eigenvalues are not necessarily distinct, but is always diagonalizable. With real eigenvalues. it is diagonalizable means that there are n eigenvectors, and eigenvectors can always be chosen to form an orthogonal matrix. Okay, so this is a very strong result, and called the spectral theorem, which means that you give me A, which is real symmetric. I must be able to choose A so that it's equal to V, D, V transpose. D is diagonal, and V is an orthogonal matrix. Any question? Now let's go back to chapter 6 again, which is I've learned that there's this spectral theorem. Let's try to see whether I can use it to define yet another inner product. So A is equal to A transpose, real n by n matrix. I get UV, so these are in Rn. I try to define inner product equal to U transpose AV. If you compare with the warm-up we had last time, so you will see that there is some similarity, but now A is a very general matrix. The question is whether this is the inner product. The answer, if just stated as is no. Because let's say I just take A to be all zero matrix, take this to be all zero matrix, then U will always be equal to 0, which means U, not necessarily, and this is definitely real symmetric. And then this is not the inner product, we have said last time. But the question is whether I can impose some conditions so this indeed becomes inner product. I'll leave again to you as an exercise to check 1, 2, 3 they hold. So really it is the fourth thing, that is UU equal to U transpose AU, whether this is non-negative, and if this is 0, does it mean that U equal to 0? So these are the questions we're asking. Any question? Okay, so let's try to answer these questions. Add pages. So now we're going to use the spectral decomposition. Spectral decom. So A, instead of this Mobius form, now we're really using the spectral decom. So, so this A must be able to be diagonalizable. So D is lambda 1, lambda n. They're real numbers. Now I look at UU. This is equal to U transpose V, D, U, V transpose U. Right? I group this part and this part. I call this one W. W is V transpose U. Then W transpose is nothing but the U transpose V, which is here. So this is W transpose D W. What is W transpose dW? Write in the component form. This is Wi squared lambda I. I want this to be a non-negative number. This is already non-negative. So all the lambda, the eigenvalues must be non-negative. You see, this condition is very non-trivial. We're not saying A12 is non-negative. We're not saying, I mean, the matrix, all the entries must be non-negative, so on and so forth. But we're saying the eigenvalues must be non-negative. So this answers the question 1. Question 2 is if UU is equal to 0, we should be able to deduce that U is 0. But let's say that we first deduce W is 0. If one of the lambda i's is 0, then we're screwed again, because that corresponding W can be non-zero, and therefore we couldn't say use a non-zero vector. So what we really need is not only lambda i's are non-negative, but they should be positive. If they are positive, then if UU is 0, this means Wi is 0 for all I1 to n. But the W is V transpose U. V is invertible. So V transpose U equal to 0 means that U is 0. So inner product. So you can see that when I defined this thing, it wasn't clear at all whether this is inner product. And this is really the proper generalization of the Euclidean inner product when you have really arbitrary matrix A there. And it says that A, all the eigenvalues must be bigger than 0. And there's actually, because there's actually a mathematical notation there. It's almost like a bigger than, and it spells as, it pronounces as A is positive definite. In other words, if I say a matrix A is a positive definite, it must mean, first of all, it is a for our purpose, real symmetric. If it's a real matrix, then if all the eigenvalues are real, are bigger than 0, then we say A is positive definite. And this case, when all the eigenvalues are non-negative, and we write A just like almost like a bigger than or equal to, and in this case it pronounces as A is positive semi-definite. Positive definite matrices and positive semi-definite matrices play an enormously important role in many fields, especially, for example, if you take the course of convex optimization, and it is all about all sorts of positive definite matrices. Any question?
Professor, why does the eigenvalue has to be positive?
This is what we explained there. And if one of them is not positive, let's say if it is 0, then you won't have u equals to 0, which is length equal to 0, then the vector is 0. Because I can just make, let's say, lambda 1, 0, all I need to make is make u1 to be non-zero, which is a non-zero vector, but its inner product with itself remains 0. Any other question? Okay, so we have finished today's lecture, which is 7.1, the spectral decomposition. And on on Wednesday, we're going to talk about another thing, which is a singular value decomposition. Again, another decomposition that is very, very useful in practice. Okay, but so